Okay, so this is then the Year 7 Light Reverse the Classroom. And what this is, it's picking up that knowledge before you actually do the light task or the light unit itself. Now the way it's spread out, you've got Year 7 Light, we then talk about transverse waves, we talk about reflection, we talk about refraction, we go through the structure of the eye, and then what we do then is we talk about the spectrum and filters, and at the end of it there's then testing and the unit at the end. Now, a few definitions first. Transparent, right, is where an object allows all light to pass through. So, for example, glass. Opaque means no light can pass through. So, for example, a brick. Translucent allows some light to pass through. For example, sunglasses. Okay? And one of the biggest things about science is making sure that what you do is you use the correct terminology every time. Now, light travels in straight lines. Now, before I do that, right, what we've got is we've got light and we've got sound. Okay? Light travels at 300 million meters per second, which is pretty quick. Sound is way slower and it travels at approximately 342 meters per second at 20 degrees C. So what happens is light travels in straight lines. So light comes through the sun, it hits a leaf, and then it travels in a straight line into the eye, to the back of the eye. Okay, put your little arrows on showing what direction it's actually traveling from. Now light is something called a transverse wave. What you do is you've got peak, you've got trough. Amplitude is the height of the wave, and it kind of goes from the middle line, right, to the top of a peak, or it could go from, to the bottom of a trough, or it could go from the middle line to a peak. And wavelength is from a peak to a peak, or it could be from a trough to a trough, or it could even be from that point on the wave there to the corresponding point on the next wave there. That's our wavelength. Now this is then reflection. And what we have is angle of incidence equals the angle of reflection. So it kind of makes sense. A beam of light comes in, right, obviously this is a straight line, hits a mirror and it reflects off. And what you've got is you've got your arrows on there. This is the incident ray and this is the reflected ray. And the angle of incident should be exactly the same as the angle of reflection. And then you've got the normal line that's 90 degrees to the mirror at the bottom. Right, now what we're doing, we're talking about refraction. We've got a glass block or a perspex block here. We shine a light, which is called the incident ray, to the perspex block. And what we've got here is we've got something called the normal, which is a right line that then comes off. This angle is called the angle of incidence. When it reaches the glass block, what it does, air, right, is lower density than glass. So glass is higher density, right? And refraction is all about the density. So the incident ray comes in, it goes from a low density to a high density, and what it does is it goes towards the normal. Okay, so it gets to this point here, it gets to this point here, it hits that, and because it's going from lower density to high density, it turns towards the normal. That's its bending, which is then where this angle of refraction, the R, is then smaller than the angle of incidence. It then carries on through the glass block, and it gets to this point here. That is then the angle of refraction again. And because it's now going from higher density to lower density as it goes out, it emerges, and the angle of incidence here is then exactly the same as it was. So it goes from high density to low density, it then turns away from the normal, and that is then the emergent ray. But you've also got to notice, right, that line there and that line there, so the ray going in and the ray coming out are parallel. Lenses. Okay, two types of lenses here. We've got convex and we've got concave. I always remember concave because concave goes in, right, like a cave goes in. If you're asked to draw ray diagrams, what you do is you've got 3 rays. That one goes straight through the middle. That one comes in and goes to the middle of the lens and bends, and this is then the focal point, focal point, and this one then comes in and it bends and goes through exactly the same point. So that point there is the focus. With a concave lens, it does the opposite. It kind of comes in here and it bends out. That one goes straight through, that one goes to there and it bends out. And also don't forget, just like I've just missed off there, there's your arrows to show the direction that light is travelling. Structure of the eye, right? So what I've got here is I've got a picture of the eye. If I start, where shall I start? I'll start at the front. I've got the pupil, which is then the hole, the black bit in the middle of your eye. We've got the cornea, which is then the kind of the tough protective layer on the outside of the eye, that if you poke yourself in the eye, that's the bit you touch. The iris is the coloured bit. The lens is kind of this part here, the bit in orange, which focuses the light. Ciliary muscle, right, is the muscle that then changes the shape of the lens. And suspensory ligaments hold the lens in place. And then at the back of the eye, you've got your retina, which detects it all. Even though this isn't labelled at the back there, that is then the optic nerve. Now, the way that you actually see, okay, I'll change it to, what colour shall I do? Blue. Right, light enters the eye through the cornea. Right, so light comes in here, and what it does, it goes through the cornea. The amount of light entered, right, the eye, is controlled by the pupil, which changes size. So this part here, that there, and that there is the pupil, and what it does, it changes the size. That's like the black hole. The lens focuses the images, or focus the image by changing its shape. So the lens here, what that does is it focuses the image that you're looking at. So if you're looking at something a long way away, it will change the shape. And if you look at something close, it will change shape, right? And what it does is it focuses it on the back of the eye. Now, weirdly, if I've actually got me there, right, what actually happens is the person or the image actually gets turned upside down on the back of the eye. The information then travels down the optic nerve, right? And because the brain is incredibly clever, what it does is it flips the image so we then see it as normal. Colours. Okay, so what we've got here now is we've got primary and secondary colours. The primary colours are your red, green and blue. So your blue, red and green. They are then the 3 primary colours. Secondary colours are then the colours that are a makeup of a combination of 2 of either blue, green, yellow, etc., etc., making yellow. The ultimate colour in the middle there is white. And we'll talk about that in a second. Now, what a prism does. A prism has the ability to turn white light by refraction in a prism into red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Or Richard of York gave battle in vain. What that does, it tells you or reminds you how you actually do the colours of the rainbow. Now, how do we actually see colour? Right, so this first diagram here, right, what we've got is we've got white light shining in. If white light hits a white surface, everything gets reflected, and what we do is we see it as white. So white light shines in, white light gets reflected because all of the colours then get reflected. What I've now got here is I've now got a red surface. If all the colours of the rainbow shine in, white light, what happens is the red surface absorbs all of the colours. So Richard of York gave battle in vain. So the red surface absorbs all of them, and the only one that isn't absorbed is the red. So what we do is we see it as red. If you've got a red surface, and this time all you do is you shine blue light onto it, like that. Because the red surface absorbs orange, yellow, green, blue, indigo, violet, it absorbs the blue, and therefore there is no colour reflected at all. Now this diagram on the right hand side, the reason why we see that as yellow is because Richard of York gave battle in vain. The yellow means that those and those are absorbed, so the only colour reflected is the yellow. The red is only seen because the only one reflected is the red. Black, Richard of York gave battle in vain. The black absorbs red, orange, yellow, green, blue, indigo, violet. So no light is reflected. Now, filters. Filters are cool, right? So what we've got here is we've got white light. This is all white light, which is the 7 colours of the rainbow. A red filter absorbs all the colours except for red. So red. A blue filter absorbs all the colours except for blue. A green filter absorbs all the colours except for green. Now, a magenta colour or filter absorbs all the colours except for red and blue, which is the 2 colours that make it. Cyan filter, green and blue. Yellow filter, red and green. Right, now what we've got here is we've got the German flag. Okay, it's the flag that we had previously. We've got black, yellow and red. What we've got here is we've got our white light going in. Richard of York gave battle in vain. Right, and all the colours then hit a red filter. Now the only colour then that goes through is red. Now with the black, because the black absorbs all colours, what it does, it stays black. Now because yellow is a combination of colours, what happens is the red hits it, and because yellow is made up of red, red is given off. And because red is there as well, red is also given off. Now, your questions. What are the 3 primary colours? 3 answers. What are the 7 colours of the rainbow in order? 7 answers. Draw and label a transverse wave. Okay, so what you're going to be doing is it's going to look a bit like that, but you're going to do it better. What is opaque? A definition. How fast can sound travel? A number plus units. Now, the idea is that you are now going to have understanding of the topic all to do with light.